Hey everyone, welcome to This Explainer. Today, we're diving headfirst into what is, without a doubt, the most extreme, mind-bending, and absolutely fascinating phenomenon in the known universe. We're demystifying black holes. Now, I'm absolutely pumped to guide you through this, because once you really grasp the mechanics of what's happening out there in the dark, well, the universe just gets infinitely more fascinating. We've put together a great visual breakdown to take us way beyond the basics and really look at how these cosmic titans actually operate. So let's get into it. I want you to kick things off by just imagining this for a second. What actually happens when gravity breaks? Imagine a place in the cosmos where the fundamental laws of physics, the literal rules that govern how we walk on Earth or how planets orbit the sun, they just stop making sense. Picture a pocket of space so impossibly dense that space and time themselves just completely fold inward. It sounds like pure sci-fi, right? But it's not. This is a very real, very physical reality happening right now, scattered all across the cosmos. Okay, part one, the ultimate cosmic mystery. Let's get right to it. Okay, let's dive into this. It's time to strip away all those sci-fi tropes like, no, they aren't giant cosmic vacuum cleaners aggressively sucking up everything in the universe. Let's ground this in actual astrophysics. Here's our anchor for this entire explainer. A black hole is, by definition, a region of spacetime where gravity is so incredibly strong that literally nothing, not even light, can escape its pull. You've probably heard the classic analogy, right? Like a heavy bowling ball sitting on a trampoline. But what happens when that mass is so incredibly staggering that the fabric of spacetime just completely sags vertically? It's not a literal hole. It is a massive concentration of matter packed into an impossibly small space, warping everything around it. So how on earth does something like that even form? That brings us to part two, birth of a monster. Black holes don't just magically pop into existence. They're forged in some of the most violent, chaotic cosmic deaths you can possibly imagine. It all starts with a massive star, way bigger than our own sun. Now, for millions of years, this star is doing a delicate balancing act. Gravity is constantly trying to crush it inward, while nuclear fusion in its core pushes outward, holding it up. But then, we hit step one. The star simply runs out of fuel. The fusion stops, and suddenly, gravity wins. Moving to step two, the core completely collapses inward on itself under its own staggering weight. And this happens in just a fraction of a second. This immediately triggers step three, a supernova explosion. This is one of the absolute brightest and most catastrophic events in the universe, blasting the star's outer layers deep out into space. And finally, step four, what's left of that core is crushed down so densely that it becomes a black hole. Literally, a monster born from the ashes of a dying star. Let's move forward and see how this builds, because not all black holes are created equal. We generally split them into two main camps. First up, stellar black holes. These are the ones we just talked about, born from a collapsed star. They're heavy, packing the mass of anywhere from 3 to dozens of our suns into a space roughly the size of a city. But contrast that with the second category, supermassive black holes. Their origins are a bit murkier. They likely form right alongside the galaxies they inhabit. And their mass, we're talking millions, sometimes billions of times the mass of our sun. The difference in scale is just absolutely mind-boggling. It's literally like comparing a single grain of sand to a massive mountain. But what actually makes up the anatomy of these things, whether they're stellar or supermassive? Well, let's look at part three, anatomy of the abyss. Let's just slow our pace down a bit here because we're metaphorically traveling right up to the edge of the void. As we approach a black hole, there is this invisible boundary that we need to be acutely aware of. It's called the event horizon. You can kind of think of the event horizon as the black hole's surface, although it's not a physical surface you could ever actually stand on. It's purely a mathematical boundary. It is the absolute point of no return. Once you cross this line, the black hole's gravitational grip becomes absolute. Whatever goes in stops communicating with the outside universe forever. So why exactly is it the point of no return? Well, it all comes down to this massive number right here, 299,792 kilometers per second. You probably recognize it. That's the speed of light. It's the ultimate universal speed limit. In physics, to escape the gravitational pull of any object, you have to hit a specific speed, known as escape velocity. For Earth, it's about 11 kilometers per second. Easy enough for a rocket. But at the event horizon of a black hole, gravity is so unimaginably intense that the escape velocity officially exceeds 299,792 kilometers per second. And since nothing in the universe can travel faster than the speed of light, escaping the event horizon is a literal physical impossibility. Cross that line and your fate is completely sealed. Which brings us to a slightly terrifying but incredibly fascinating question. What would actually happen to your physical body if you fell in?
Part 4. The spaghettification effect.
Okay, so if you were unlucky enough to fall feet first toward a stellar black hole, the gravity pulling on your feet would be exponentially stronger than the gravity pulling on your head. This massive difference in gravitational pull creates what physicists call extreme tidal forces. As you get closer, these forces would start to stretch your body vertically and completely squeeze it horizontally. And yes, spaghettification is the actual, highly technical astrophysical term used by real scientists to describe this. You would literally be drawn out into a long, incredibly thin, microscopic string of atoms, basically like a piece of spaghetti, long before you ever even crossed the event horizon. It's a pretty grim, yet honestly mathematically spectacular way to go. Now, what's really interesting here is how relativity completely distorts this whole reality based entirely on perspective. Let's imagine you have a very brave friend who volunteers to fall in while you stay safely behind in your spaceship. Because immense gravity actually warps time, a little concept known as time dilation, you and your friend are going to experience reality completely differently. As the observer, you'd watch your friend approach the event horizon, but they'd appear to move slower and slower and slower. Eventually, to your eyes, they'd appear to just freeze right at the edge, slowly fading to red and disappearing. You'd never actually see them cross. But for your friend falling in, they wouldn't feel time slowing down at all. From their point of view, time just plunges forward perfectly normally as they fall straight through the horizon and down into the abyss. It's a completely mind-bending reality where space and time become entirely subjective.
Finally, Part 5. The engine of galaxies.
Let's zoom out from that terrifying individual perspective for a second. Let's look at the massive, awe-inspiring scale of the entire universe. And this brilliantly illustrates why black holes are actually so essential to the cosmos. Remember those supermassive black holes we talked about earlier? Well, we now know that almost every large galaxy, including our very own Milky Way, has one of these absolute giants sitting right at its center. And they are not mindless vacuum cleaners destroying everything in sight. In fact, they anchor entire galaxies. They hold billions of stars in orbit just with their sheer gravitational mass. On top of that, the massive amounts of energy they release when they consume gas and dust actually regulates star formation, keeping galaxies from growing too fast or burning out too quickly. They literally shape the evolution of the universe as we know it. We simply wouldn't have the structured, magnificent galaxies we see today without them acting as these vital central engines. Which leaves us with one final profound thought to ponder today. Down at the very center of a black hole lies the singularity, a point of infinite density where all of our current laws of physics just completely break down and fail. If black holes anchor every galaxy, including the one we call home, what incredible secrets lie hidden beyond that singularity? What totally new physics, what new understandings of reality are just waiting for us out there in the dark? It is, for sure, the universe's greatest mystery, and the deeper we look, the more wondrous it becomes. Thanks so much for joining me on this explainer. Keep looking up, keep asking questions, and I'll catch you in the next one.